Hi everyone, in this video we are going to talk about the Compton scattering phenomena and we'll derive the Compton wavelength shift. So the Compton scattering phenomena is associated with the particle behavior of light. So we know now that light is made up of small tiny packets of energy which are also called photons. So what happens in the Compton scattering phenomena is that a photon of a given incident energy collides with an electron, it scatters the electron and the photon itself gets scattered in a different direction. Now, the problem statement is as follows. We know that the incoming photon has a given energy, and we want to find out the energy of the scattered photon when it is scattered at a certain angle theta. So why will the photon energy change? That is because the photon will give some of its energy to the electron, and when the photon gives its energy to the electron, the energy of the photon will decrease. And since the energy is inversely proportional to the wavelength, since the energy of the photon decreases, its wavelength will increase. So we can also call this as red shifting of the photon, which is why I've drawn this with a red line here. So this gives you an idea that the photon will give its energy to the electron, increase its momentum, and go to a more higher wavelength since it will be losing its energy. So we want to find out the change in wavelength between the incoming photon and the outgoing photon. So let's do that. So the way we go about doing this is by using momentum conservation in the system and energy conservation of the system. So let's find out what the momentum and the energy of the different particles in our system are. So for an electron, the net energy of the electron will be associated with its rest mass energy as well as its momentum of as the momentum of the electron. Now, in the initial states, the electron is stationary, so it will only have rest mass energy. But after the photon collides with the electron, or after the photon interacts with the electron, the electron will have non-zero momenta. Now, for the photon, its energy can be calculated as the product of its momentum and the velocity of light, which can be also written in the form of hc by lambda. And the momentum of the photon is from the first equation can be written as E over c. And then placing the value of E as hc over lambda, we can get the momentum of the photon as h over lambda, where lambda is the wavelength of the photon. This is also the de Broglie relation for the wavelength of a photon. So let's just mention that here, de Broglie wavelength relation. So now let's go on and use momentum conservation and energy conservation for this problem. So let us start with momentum conservation first. So first we have momentum conservation. So in momentum conservation, we can see that initially only the photon has a non-zero momentum which associates to momentum p1. But when it interacts with the electron and it gives some of its momentum to the electron will have a non-zero momentum pe, while the photon will change its momentum from p1 to p2. So we can write momentum conservation as p1, which is the initial momenta, as equal to p2, which is the final momentum of the photon, plus pe, which is the final momentum of the electron. All these three are vector quantities, so we must not forget the vector symbol. So if we want to calculate pe, we can rearrange the equation and write pe is equal to p1 minus of p2. And if we want to calculate pe dot pe, and both of these are vectors, this will be equal to p1 minus p2 into p1 minus p2. And what will happen now is that left side of this equation can simply be written as pe squared, and on the right side we'll break this down and we'll have p1 squared plus p2 squared minus 2 p1 p2 cos theta. And this comes from the dot product of these two quantities. So since these two are vector quantities, when we multiply them we'll have to take the dot product. So we'll have p1 square plus p2 square, and then the middle terms for the middle term will be minus 2 p1 p2 cos theta. So this is all the information we can get from the momentum conservation of the system. So let's go with energy conservation and we'll see what information we can get from there. So in energy conservation, so when we write the energy of the photon, we'll use this relation for the photon, and for the energy of the electron, we'll use this relation. So let us do so. First, let us calculate the initial energy of the system. So the initial energy of the system corresponds to the energy of the photon. So the energy of the photon initially, let's say, is hc over lambda 1, where lambda 1 is the initial wavelength of the photon. So we'll just write that down. Lambda 1 is initial wavelength, and lambda 2 we'll call the final wavelength, is our final wavelength. So in our energy conservation, we'll have the energy of the photon hc over lambda 1 plus the only the rest mass energy of the electron, which will be m naught c square. And then in the final stage of the system, we'll have the energy of the photon, which will be hc over lambda 2, where lambda 2 is the final wavelength. And this time we'll have energy corresponding to the rest mass of the electron as well as its momenta, which will be pe square c square, and we'll take the square root of this. So this is our energy conservation equation. Now we want to simplify this equation and get it in a form similar to what we got in the momentum conservation form, and we'll see why we want to do this. So when we write h over lambda 1, we know that p is equal to h over lambda. So we can also write h over lambda 1 as p1, and p1 is the initial moment of the electron. So this will become p1c plus m naught c square. And similarly on the right side we'll do this, and oh sorry, this was supposed to be lambda 2, and so on the right side when we do this we'll get p2c plus m naught c square plus pe square c square raised to 1 by 2. Now what we'll do is we'll take the p2c term on the left hand side and we'll take the square on both sides of the equation. So what we end up getting is um, m naught c square plus c square p1 minus p2 the whole square plus 2c m naught c square p1 minus p2, and this entire thing will be equal to m naught c square plus pe square c square. So all we've done here is take the p2c on the left side of the equation and take the square on both sides of the equation, and I've already expanded the square that will arise on the left side of the equation here. So now what we'll do is we'll divide the entire third equation that we got here. We'll divide this entire equation by c square. So we'll just be left with pe square is equal to p1 square plus p2 square minus 2 p1 p2 plus 2 in m naught c p1 minus p2. Notice in this equation we cancel out the m naught c square on both sides of the above equation, and we've written the pe on the left side of the equation instead. Now what we'll do is from the third and the fourth term right here, we'll take out 2 p1 p2 common from both the terms, and this is because we can already see some resemblance between our momentum conservation equation and our energy conservation equation. We have a pe square, we have a p1 square, we have a p2 square, we also have 2 p1 p2, but we also have a fourth term. So instead what we'll do is we'll take out 2 p1 p2 common from the third and the fourth term. So let's do that. We'll do that, and when we take out p2 p1 p2 common, what will be left with is equal to, inside the bracket we'll have 1 minus m naught c 1 over p2 minus 1 over p1. Now the time has come to compare these two equations. We are comparing the momentum conservation and the energy conservation system, and from this when we compare, we'll simply compare the value of cos theta with what we have inside the bracket here. So this can be simply written as cos theta is equal to 1 minus m naught c 1 over p2 minus 1 over p1. Now what we'll do again is we'll rearrange this, and we'll write instead m naught c 1 over p2 minus 1 over p1 is equal to 1 minus cos theta. Now again with with the momentum of the photon, we know that the momentum of the photon can be written as h over lambda. So we'll do that, and when we do that, we can write it as m naught c lambda 2 over h minus lambda 1 over h is equal to 1 minus cos theta. And when you take out the Planck's constant h as common and multiply it on the other side of the equation, what you'll be left with is lambda 2 minus lambda 1 is equal to h over mc 1 minus of cos theta. So this is the final wavelength shift in the Compton scattering phenomena. And we can see that this wavelength shift is dependent on the theta of the photon scattering. So what will happen is the higher the theta, or the higher the photon is scattered when it interacts with the electron, the higher the wavelength shift. So higher the cos theta, this term will increase since cos, and then the wavelength shift will also become larger. So let's get a graph here and we'll roughly see how this phenomena looks, what this phenomena looks like. So this is a graph corresponding to the Compton scattering phenomena. On the y-axis of this graph, we have the photons that are detected in an experiment, and on the x-axis we have the wavelength axis. So what will happen is when the photon will interact with the electron, it will get scattered at different angles, and based on what angle it is getting scattered at, it will have a different wavelength, and the wavelength shift will be different for different theta, which is also evident from the equation that we just derived. So when theta is equal to 0, the wavelength shift will be equal to h over mc, and we can barely differentiate between the incoming photon and the outgoing photon. When the theta increases to 45 degrees, we can clearly see two separate peaks right here, and the first peak corresponds to the incoming photon, since it has a lower wavelength, and the second peak corresponds to the outgoing photon, since it has a higher wavelength. And we can see that as theta increases, what will happen is this term will increase and the wavelength shift will also increase. So the two peaks of the incoming and the outgoing photon get wider and wider, since the wavelength shift of the incoming and the outgoing photon will also become much larger. So that is all we'll cover in this video. If you have any doubts or suggestions, please leave them in the comments down below. If you like the explanation, please give this video a thumbs up, and thank you for listening.